issues in statistical inference. So here I wanted to talk to you about some issues in statistical inference. And we're not going to talk about all of the issues. There are too many. But let's address some major ones. And one has to do with, well, what if we don't have the data? We simply don't have the data, or we don't have sufficient data, or we don't have data that um, addresses all those specific, sometimes rigorous requirements to enable us to make these causal determinations about relationships in the world. I have an example here that has been in my mind recently, which has to do with ozone therapy. So if you go to Wikipedia, they say something about ozone therapy. Ozone, you can see the keywords. Ozone is a toxic gas. That's the first thing they focus on, with no known useful medical application. And then it says pure quakery and so on. But if you actually look into the studies on ozone and ozone therapy, there are hundreds, if not thousands, of studies showing the effectiveness of different types of ozone therapy for all sorts of condition. Now, is there, randomized controlled trials, they call it, the big controlled trials that you would expect or you would want, that would give you such strong evidence that one intervention or one therapy is actually producing the effects of interest? I'm not sure, maybe not. But so that's the issue, right? How much can we have confidence in our studies, in our data, given the kinds of studies we have? And how much are you willing to accept some kind of information based on the types of studies and the type of evidence that we have? Is this sufficient data? Is this enough data? Are these studies conducted properly, and are they sufficient? So it's not just are we don't. What if we don't have the data, or the quality of the study that we determine, we ourselves, whoever determines, that we want? Although, of course, most people would agree that these randomized controlled trials are the most effective experimental and reliable evidence for any kind of intervention. But they're difficult to do. They're expensive, and many things in the world is just impossible to do these studies in this way. Um, Sometimes statistics itself, the statistical inference, is not the right approach. And I'm going to share with you this very brief paper about teaching statistics, talking about how we can see that maybe storks do deliver babies. So storks, that kind of bird associated with delivering babies in fairy tales and children's stories and in traditional stories. And the article goes into the issue of, well, you can, if you're taking a statistical approach to look into how storks deliver babies, you see the data there, and you see kind of a correlation between the number of storks and the number of births that there have been. And it's a linear, it looks like a linear correlation, a positive linear correlation. The more storks there are, the more babies are there. So you cannot disprove that storks are not related to baby deliveries, but the whole question is, well, is this even the right approach, right? That's the what I was thinking. Why would we even take this approach to address this question? Why don't you examine the mechanics of how babies are delivered and so on? But if but there is also something true about the data, so we have to be careful about that. So no, there is a statistical relationship, and it's a strong statistical relationship, with very low p-value, meaning that we do see that relationship is probably, we can be confident in that relationship we're observing. But there's confounding confounding factors. Another factor that is moving in the same direction as these other two, another factor that maybe is impacting storks and is also impacting babies, but it's not that these two are together, is that there's another confounding factor. And another one that they raise, of course, is just land areas of the areas that they are measuring these things. So the higher the land, the higher the area, then the more babies, and they're also the more birds. So that can be a confounding factor implicating the relationship between these two, and we'll also have to be careful about that. Once again, kind of mentioned this before. For example, in the example of ozone therapy, what if other people don't like the smell of your methods? They don't like the quality of your methods. They just say, I only like this method, I only like quantitative methods, and I don't accept your other methods. You don't have the most expensive and sophisticated methods. So is your research reliable? Is your research valid? That's another problem with statistical inference. Most researches are not big randomized controlled trials. So should we believe them? Should we how much value should we put into them? And there are many other issues. One here that might be of interest, but goes into big data and other methods we're not dealing with in this class, and what these authors here call big data hubris and algorithm dynamics. So they're looking into the Google flu trends application and algorithm that was trying to predict flu based on people's searches about flu, and it came out actually pretty wrong in its prediction. And they're in this article they're talking about, wait, why did it predict so wrong? Well, one has to do with this uh, big data hubris, which is the reliance on just large amounts of data, and only relying on large amounts of data and forgetting about all those characteristics that we talk about here regarding the need for proper study design, independence between the variables, uh, making putting thinking of variables that are logically and valid related to each other. So for example, you can see that storks and babies, the number of storks and babies, they go together, right? The more the storks there are, the more babies. So well, does that mean the storks are delivering babies? Not necessarily. So when we're dealing with big data and these new approaches to statistical inference, they often forget about what the data is. They're just trying to predict. So they just put more and more data. So any relationship that can show them a prediction, it doesn't matter if it's college football games that are in more college football games, there are maybe the more flu there are in population where they don't even play college football. It doesn't matter because it's predicting. So that's the kind of issue that they're addressing over here, and so part of the issues with statistical inference today. I'm going to leave you with this for now, and we'll continue next time.